Welcome to Session 14, Exponents and Scientific Notation. This lesson strengthens algebra that remains reliable when the numbers or representations become unfamiliar. You will learn to apply exponent laws only to matching product or quotient structures, to rewrite negative powers without changing coefficients, and to interpret exponential growth and decay factors in context. Treat these as connected habits. Keep a pencil ready. We will build a visual model, use a repeatable process, solve a demanding example, diagnose an error, and finish with a checkpoint. Start with this picture. Decimal movement and powers of 10 change in opposite directions while preserving value. Each decimal shift is paired with an opposite exponent adjustment. In algebra, multiplication, division, and power of a power are distinct structures requiring different exponent operations. The key distinction is this: apply exponent laws only to matching product or quotient structures. Then connect it to the second goal: rewrite negative powers without changing coefficients. Correct methods begin with correct interpretation. When a problem looks different, look for the same mathematical structure instead of an identical example. That transfer makes the skill durable. Step 1. Identify the outer operation before choosing an exponent law. Identify the object being changed and the requested result. Step 2. Apply powers to every factor inside a product. Use a separate line so signs, units, and restrictions stay visible. Step 3. Move negative minus power factors across the fraction bar. Work efficiently without skipping an operation. Step 4. Normalize scientific notation and interpret the growth or decay factor. Whenever possible, verify with evidence independent of the original working. Signal 1 is same base multiplied. Respond by remembering add exponents. Name the response before calculating. Signal 2 is power raised to a power. In that case, multiply exponents. The form tells you which tool fits. Signal 3 is percent change repeated over time. Remember, use 1 plus r or 1 minus r. This separates plausible from valid answers. If you cannot name the signal, slow down. Deliberate classification is faster than repairing rushed algebra. Here is the challenge. A quantity follows a equals 640.5 to the power t/3. Find and interpret a when t equals 9. Restate the target and identify the most important part of the routine. The first move is substitute a equals 640.5 to the power 9/3. This changes the form without changing the meaning. Next, the exponent is 3, representing 3/2 minus life periods. Keep the relationship visible and apply the operation to every required term. Now audit distribution, signs, copied values, and restrictions. A brief midpoint check is cheaper than rebuilding the solution. Continue with the third step. Compute 640.5 cubed equals 640 over 8 equals 80. State what the transformed line tells you. Complete the argument. After 9 time units, 80 units remain. This is part of the solution, not decoration. The final answer is 80 units. Compare it with the requested variable, expression, unit, interval, or classification. Verify from another direction, substitute, compare representations, inspect units, or test a boundary. Prove that the result satisfies the original conditions. Try this checkpoint without copying the example. Simplify x cubed to the power 4. Decide which mathematical fact controls the answer. Write one line of reasoning before you commit. A visible decision is easier to inspect and correct. F-focused hint. A power raised to a power multiplies exponents. Use it to repair your setup rather than guess. An accepted answer is x to the power 12. Explain why it works and name the first step that would expose a common error. The central message is: apply exponent laws only to matching product or quotient structures. Combine it with the discipline to rewrite negative powers without changing coefficients. Finish by remembering to interpret exponential growth and decay factors in context. This turns a calculated result into a justified answer. Reflection. Why does 12% decay use 0.88 rather than 0.12 as its repeated factor? Name the error specifically so you can interrupt it next time. Practice one fresh problem within 4 minutes, including a contextual sentence. Keep the work readable, check it independently, and carry the routine forward.